Okay, so let's talk about nuclear radiation. First thing that you really need to know for nuclear radiation is about isotopes, and in particular what are called radioisotopes. So just as an example, let's say that we had hydrogen with one neutron and one proton, and of course one electron as well to keep it all neutrally charged, spinning around. Now we can have isotopes of hydrogen, so two neutrons, deuterium, or three neutrons, tritium. And there are other isotopes as well. But there are certain isotopes called radioisotopes which are not stable. So that is, the setup for that atom is not particularly well liked by the atom essentially, and it wants to lose some of the mass and some of the energy. So it does that by decay. And there are three types of decay we can have. Now they're called nuclear decay or nuclear radiation because they're to do with the nucleus, that part of the atom in the middle. And the three types of nuclear radiation we can have are what are called alpha, beta, and gamma. And they're to do with different types of particles with alpha and beta, and gamma is in fact energy, so gamma rays. So I guess in this video I've highlighted the really key things you want to take note of in your books, which are in these blue rectangles. So I've taken these notes out of your book. I'm going to talk you through the rest of it, but the key things are in the blue rectangles. So in terms of energy, the main unit of energy that we use in this text is the joule, but we're going to be looking at electron volts when we deal with nuclear radiation. So an electron volt is the amount of energy gained by an electron when it's accelerated across a 1 volt drop. And for us with nuclear radiation, we actually use the mega electron volt, so it's MeV. That's the notation. The mega electron volt is 1 million electron volts and is equal to 1.602176 by 10 to the negative 13 joules. And when we talk about nuclear radiation, usually we have energy between 0.1 to 10 mega electron volts released. So the first type of nuclear radiation and nuclear decay that we're going to look at is what's called alpha decay. So alpha decay is where you have a nucleus. So this is the diagram down here. You've got a nucleus that actually ejects a helium nucleus. And you can see here that this helium nucleus has two neutrons. It has two protons. But can you see that it has no electrons? Because it's actually just a nucleus. It's not an atom, it's a nucleus. So what that means is because this particular particle here has two protons, it actually has a positive charge on it. And they discovered that by finding that they could deflect this particle in magnetic fields, or electric or magnetic fields. So the fact that this has a charge is actually quite important. When we lose this nucleus, this helium nucleus, two neutrons, two protons, we actually have two things being lost, the nucleus and also a bit of energy, because remember this thing's moving really quick. So we also have, I'm just going to use a little E for energy coming out of this reaction as well. So we can see here we start with the original nucleus, we end up with the alpha decay, we lose energy and a helium nucleus, so two protons, two neutrons, and this nucleus here that we have left over is what we call the daughter nucleus. So this nucleus now has two neutrons and two protons less than what it started with. So often with nuclear radiation, you end up with atoms that actually degrade in a lot of ways. So you might have like alpha decay and then beta decay and maybe more alpha decay. And it's sort of like this chain reaction until you get to a point where your atom that you originally start with actually becomes stable. And that might be a lot of different versions of decay down this track. So here, alpha decay, it's all about losing this little thing here. And the cool thing is this helium nucleus is what's called the alpha particle. So this guy here is the alpha particle. All right, so you can see in an example here you've got a equation. So you've got uranium, so 238 uranium, atomic number 92. It is degrading by alpha decay. So what happens in alpha decay is that it loses two protons. There's actually something wrong with this. This is from the textbook, but it's actually wrong. That should be a 0, like that one. So you've got losing two protons and then losing two neutrons as well. So see up here, this is a 4. That's because remember this is the mass number, and the mass number is neutrons plus protons. So if we've lost two protons and we want to lose two neutrons as well, we have 4 altogether up there. Okay, so when you look across this equation, what you need to take note of is that these numbers at the bottom, the 92, 90 plus 2 equals 92. So these added together should give you what was on the left side. And also these top numbers, so the 238, the numbers on the top, 234 and 4, they add together to give you what's on the left. So it needs to balance. And we also have that energy, it's kinetic energy that's lost by movement of this alpha particle being ejected. So this is an alternative version of the same equation, but you can see here instead of writing the helium nucleus, they just write an alpha for alpha particle. All right. So we're going to just do a sample problem down here. I'm going to do this in a green box. So I'll do all the sample problems in a little green box. Okay, so the question's asking here we're going to try and figure out the alpha decay equation. So we've got gold, Au. It's got atomic number 92, mass number 234. It's going to 230 Th, which is thorium, and 90. So you can see here underneath, see we've got 90, we're actually 2 off. So what I do is have a 2 here, 90 plus 2, well, that's 92, so that matches. And then I need 234, so I've got 230, so I need a 4. 230 and 4 is 234. And we know 4, 2, well, that's a helium nucleus. So that means this is going to be, I'm just going to use my little E for energy, that's going to be alpha decay. And if you wanted to, instead of writing helium, you could actually just write that as alpha. It's an alpha particle, like that. That's totally fine. Okay, so next type of decay that we're looking at is beta decay. Now there's 2 types of beta decay that are possible. Remember, I've put the key things in the blue boxes for you to write in your notes. So there's beta minus decay and beta plus decay. So we're going to look at beta minus decay first. And the idea with beta decay is you've got something going on in the nucleus, yeah? So you've got in the nucleus neutrons and protons, and they actually spontaneously turn into something else. So in beta minus decay, you have a neutron. What happens to the neutron is it splits into 2 things. A proton, which remember has a positive charge. So in order to make it still neutral, because you should still have neutral overall neutral charge, it splits into a proton and also an electron. And the way we write those things is P, 1, 1, because it's got atomic number 1, effectively, 1 proton, and the mass is 1. And an electron has no mass, because it's so tiny, but it has a charge of -1. So we have this formula here, which is neutron, 0, 1. Remember, it's 0 down here because there's no charge. 0, 1 neutron goes to a proton, 1, 1, plus an electron, -1, 0. And when we talk about this beta decay, this actually is 1 neutron turns into a proton plus what we call a beta minus particle. So this little electron is actually what we call a beta minus particle. Okay, and when we talk about the parent nucleus and what it splits into, the parent nucleus splits into a daughter nucleus, which still has this proton inside the nucleus. Okay, so that proton doesn't move. So let's pretend this is neutrons. So a neutron splits, it now turns into another proton, and that proton stays in there. But the electron, the little guy, make him green, he splits off. He's the beta minus particle there. So these 2 things equate to this neutron that you had at the beginning. So that's beta minus decay. So an example of beta minus decay is here, and I should put this actually in a blue box because you want this one in your notes. It's a good example, and probably the sample problem too. Alright, so we've got this example, we've got thorium, thorium 234, so it's atomic number 90 because it's 90 on the periodic table, and that turns into Pa, which is protactinium, so protactinium 234. You can see here that the mass number didn't change, right, and that's because we're ejecting an electron that has no mass. So because we're doing that, that top number doesn't change, but the bottom number does change, and you can see here it actually increases, whereas before with alpha decay it decreased. And that's because you've got this -1 coming from the electron. So on the right side, remember that the bottom number's on the right side, 91, and the bottom number here, -1, so 91 take away 1 should equal 90, which it does. And the top numbers, 234, that's 234 and 0, so they equate. So this is an example of beta minus decay, and we have energy as well that comes out of that reaction, just as it does with alpha decay. So the sample problem here, we've got Pb, which is lead, and Bi, which is, I think it's bismuth. I'm just going to double check it. There's lead. Yeah, bismuth over here, 82 and 83. So we've got 210 lead goes to 210 bismuth plus something. Here we've got an 83, here we've got an 82. So that means my equation must have been lead goes to 210 bismuth, 83. To make it match, I need to take one off this to get it to 82, so it's a negative one. These are still the same though, so it must be a 0. Oh, that's an electron. And if it's an electron, we also have energy. And if you like, you could even write this without using the electron. So you could write this, or, and I'll just do the other version out here, 210, 82, lead goes to 210, bismuth, 83, plus a beta minus particle, plus energy. So that's beta minus decay. Now you've probably figured out already what beta plus decay is. It is very similar, but instead of us shooting out an electron, we shoot out this thing called a positron. So remember, important stuff is in the blue box. So again, in the nucleus, you have instead of a neutron turning into a proton and an electron, we actually have a proton turning into a neutron and a positron. So for example, we have a proton, it's a plus, turns into a neutron, which we know is 0 charge, and this little guy called a positron. Positron. And he is positively charged. In terms of the notation, the neutron, again it's 1, 0. This little guy, the positron, is sort of like an anti-electron. So he's still a little e, no mass because negligible mass, but a +1 charge. So we've got proton turns into a neutron and a positron. So an example of beta plus decay is from sodium 22 decaying into neon 22. And you can see at the bottom here we've got sodium with atomic number 11 turns into neon, atomic number 10, and then you've got this little +1. And that's because you need, remember, the bottom numbers on the right side have to equal the bottom numbers on the left. So 1 plus 10 is 11, and then on the top you've got 22 and 22, so that has to be a 0, negligible. So this is a positron. All right, and you can write that. The other way of writing that would be sodium 11, 22 goes to neon 22, 10 plus a beta plus a positron plus energy. So this is a sample problem here. So we've got carbon, so carbon 11, and we've got B, so boron. And we need to figure out the type of decay. So we can see here, I'm just going to write it out, 11, 6 goes to 11, 5, B. So add these, look at these things, you go, okay, well, that's a 6, that's a 5, that means I need one more. 11 and 11, they're the same, so no more mass. Oh, 0 plus 1, that's a positron. So it's always a good idea to really do those sums on the bottom to figure out if it's an electron, a positron, or if it is alpha decay. So all the way back here, remember alpha decay? We were looking for like a difference of 2. So alpha decay is much easier to spot. And if you wanted to, the other way you could do this, of course, is for you to just call it, instead of writing it as a positron, write it as a beta particle. Done. So that's beta plus decay. So we've got just a few revision questions, and then we're just going to talk about 2 other things, neutrinos and also gamma radiation. So we've got equations here for the alpha decay of americium, so 241. So I'm just going to do these questions here. So AM 241. We do have to find where that is on the table. It's down here, which is 95. So atomic number 95. The alpha decay. So a nice way of doing these is I actually write the alpha particle first. I know an alpha particle is 4,2 helium nucleus plus energy. And that means there's something else here. So this is where I'd look now at the bottom numbers. 95. Something plus 2 has to be 95, so that has to be 93. So that helps me now. I can look over in the table and I can see it's this NP. I don't know what NP is. Let's have a look at what NP is. Ooh, Neptunium. That's pretty cool. So 93 Neptunium. And then at the top, 241 and 4. Okay, so I have to take 4 away from 241. If I took away 3 from 240, it would be 237 plus 1. So it's 237. 237 Neptunium. So that would be the alpha decay of americium. Alright, so adding the bottom and the top, they need to be the same. So the next one is beta minus decay of platinum. Platinum 197. And you can look over in your periodic table. So use your periodic table to help you because you really need to know the atomic numbers of the various things that you're working with. So I'm going to just look for 197. Oops, where are you? Where are you, platinum? There you are, 78. And usually it's going to decay into something that's near it on the periodic table as well. So 197 platinum, it's beta minus decay. So first of all, I'm going to write down my little beta minus particle, which is an electron and energy. And now I have to figure out what goes here. And remember at the bottom has to add up. So 78, something minus 1 has to be 78. Okay, so it's going to be 79. Look on my table again. 79 is gold. And the top, it has to be 197 on the top. I've got a 0 here from my little beta minus. So to make it match, this would have to be 197. It's 197 gold, which if you think about it right, how cool is this? You've got platinum degrading and turning into gold. It's pretty amazing. You can make gold from platinum by radioactive decay. And then the last one, C, is beta plus decay of magnesium. Magnesium 23. So you can see magnesium there is 12. Magnesium 23. And it's beta plus decay. So that's a positron plus energy. And we've got the bottom has to be the same. Something plus 1 has to be 12. So that's got to be 11. We look in the periodic table. 11 is salt. Sodium. So sodium and 23 and the 0 from the positron. So this has to be 23 for the top to match on each side. So 23 sodium when we have our beta plus decay. Now, of course, instead of writing it like that, the other alternative you could do is you could actually write them as their particles. So you could write them as an alpha particle, as a beta minus particle, and as a beta plus particle. All right, so we're just going to quickly talk about this little thing called the neutrino. So a neutrino is called the little neutral one, named by Enrico Fermi. It's a particle, and it came about because of experimentation when they were looking at beta decay, and they figured that they couldn't account fully for energy and mass when they were looking at beta decay. And so this little guy, neutrino, he's so tiny, he doesn't really contribute much mass, but he contributes energy. And you get neutrinos and antineutrinos depending on the type of decay. So if it's beta minus decay, which is the example that we have here, you've got your neutron turns into a proton, a beta minus particle, and energy. We call the energy antineutrino, an antineutrino. And if you have beta positive, a beta plus decay, then you have a neutrino, which is we just use a little v. So the v is nu in Greek. All right, so for example, if we go back, I'm just going to copy a couple that we've seen so far. So we've got here, this is our carbon to boron. So this is probably a nice example to have. And when we looked at our beta minus decay, we had the example of lead to bismuth, this one here. So we can write this thing out fully, both of these now out fully, using all of the notation we understand. So we can look at this carbon going to boron with the beta plus particle plus energy. So what we can really write it as now is its final form. So 11 carbon goes to 11,5 boron plus a beta particle plus, Now this is beta plus decay, so when it's beta plus decay we just use the little neutrino. This one here is the opposite. This is beta minus decay, so lead 210, 82 goes to 210, 83 bismuth, plus a beta minus or electron particle, plus an antineutrino. And if you can't remember which one's which, you see the little minus, it goes like on top of the neutrino here. So that's how you can remember that's the one with the line on the top. So they're the two, I guess, fully formed equations where you've really not written electrons and protons, electrons and positrons, you've written your particles and you've also written in your neutrinos. Last type of decay we want to look at is gamma decay. Gamma decay is a whole different ball game. This is all about energy in the form of gamma rays or photons. So this form of radiation, I'm just going to highlight that part, that's really important. So during gamma decay, a small packet of electromagnetic energy, which is called a gamma ray or photon, is emitted rather than particles. So you don't end up losing electrons or positrons. Following the decay, the arrangements of the protons and neutrons in the nucleus may not be ideal, so you may end up again losing more energy either through the loss of more gamma rays or by alpha or beta decay. So this is usually part of a radioactive chain. So an example here you can see of an excited nucleus. We tend to write them, the notation is to have a little asterisk. So if you have an excited nucleus, it's got so much energy going on, it's a little bit unstable, it wants to lose that energy through losing a photon. So it goes from being an excited bismuth with the little asterisk to just bismuth, it's just plain. Okay, the daughter nucleus now has less energy, but what you'll notice is that, see, the numbers don't change because you haven't lost any particles, you've just lost that energy. So you've gone from this excited state to a not excited state, and the loss of the gamma ray, so that's where that energy has been emitted in the form of a gamma ray. Okay, so I've just taken off Wikipedia just an example. This is cobalt and how it decays. So cobalt actually decays in 2 steps in this chain. So cobalt going into nickel. Can you see here that we've got 27 going to 28? So that means that this must have been a -1 because 28 and 20 and -1 is 27. So it lost an electron. Okay, so this actually would be beta minus decay. And then this nickel is like in an excited state. So this excited state nickel then goes down to just plain boring nickel, but it does that by losing a gamma ray. And this is interesting too because this is a real life example. You can see the mega electron volts that are lost, but also with this beta minus decay there was a gamma ray that was also emitted. So you can have like combinations as well of decay, but in this course we're really just looking at it's either going to be beta decay, straight beta decay, alpha decay or gamma decay, not really combination.